Okay, hi guys. So in this video, we're going to be watching the execution of a complete program on the SCOT CPU that's been implemented in this FPGA board right here. So just to recap, of all the modules we've implemented and presented earlier, there's three big differences I would say that we have to adapt regarding John's design. The first one is the bus. So as John explains in his book, every register and memory and all that is connected directly to the bus. In reality, you cannot do it that way because you cannot have multiple drivers for a single wire. So in this case, I used a construct called a war that basically allows you to capture the output of everything that's connected to the bus and OR it all together and create a single bus. Then there was the clock that we had to do a bit differently. Obviously, we had to use the internal clock of the FPGA to source our own clock. And thirdly, the stepper. So I could not get the stepper to work the way it's described in the book. Like I said, it's a bit sensitive to propagation delay and susceptible to race conditions. So I went with basically just a simple loop stepper that loops from 1 to 6 and alternates between the signals. Also, I implemented an I/O device here, which is this 7-segment display. So if you look at the source and you see out A instructions that send stuff to an output device, it's sending the corresponding value to this 7-segment display here to be shown. So as the computer runs, you will have clock E and clock S here on these LEDs. You will have each of the 6 stepper steps light up on these LEDs here, and this is the value of the bus. So as it runs, if you are quick, when stepper is on step 2, this is when the instruction is enabled onto the bus, and you can recognize some of the instructions here when you look at these LEDs. This program that we're going to be looking at is very simple. It's basically the same one as doing something useful that we looked before. So it's going to add two numbers, 20 and 22, and give us a sum hopefully of 42. Every time we set a value in a register, there is an out A instruction so that it comes up displayed on the 7-segment display here. At the end of the program, there is a halt instruction that I invented that basically stops the computer where it is. So I'm going to program the board now. All right, so here it goes. So we can see now that at each step, so stuff is happening on the bus. We see the various bits that are being lit up here. So soon we should see one of the instructions that's gonna so we just passed it now. Number 20 has been loaded into a register. Then we're gonna load number 22 pretty soon. Just about here, and then we're gonna go to the ALU to perform the add instruction and hopefully get a result of 42. Yes. And then last instruction, the system should stop by itself. All right, so this is the first demo of the working computer. I'm going to try to do 2 more videos. One is going to be a 5x5 multiplication that's available on John's website. And I also trying to write up a small program to compute Fibonacci numbers. So we'll see if we can get that up as well. Thank you.